Okay, in this tutorial, I'm going to give you a worked example of a question on standard deviation. Now, I'm using an older past paper format to show you this, which actually comes from the 2014 exam. The modern advanced higher is slightly different, and I'll just briefly explore how it's different as I go through this. But most of these questions are very similar to what you will encounter in an SQA exam. You might indeed choose to write some of the answers yourself prior to seeing what I have to say in regards to what a typical answer should look like. Now, the first thing to acknowledge about standard deviation is we are not looking for correlation or difference as we would be doing with Pearson tests, Spearman tests, or chi-squares. This is a statistical test that is used to describe a data set in a certain way. In the same way that the mean of a data set, also known as the average, is a single number used to describe a whole data set. Likewise, the range of a data set, which is the difference between the highest value and the lowest value, is also a way of describing a data set. So standard deviation is exactly the same. It is a statistical test that is used to help us understand a data set in more detail. And I'll talk a little bit about how, in what different ways we might choose to do so. Now, in this example, we are given the rainfall totals for July from a town in England, Cambridge, and those totals are between 2001 and 2011. And in the old format exam, you would have been asked to calculate the standard deviation. And that's not what you're required to do these days. Rather, these days, you're required to simply explain or outline what the result actually means. And let's explore that in a little bit more detail by actually having a look at the data set in question and have a think about what we're being asked to do when we're calculating the standard deviation. We'll come back to these two questions here in a second, as well as this one here in terms of the suitability of this particular test. Okay, the first thing we would really need to do is actually have a look at the data set that we're being asked to explore. So here is our data set. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 years worth of data in this data set. Okay. Now, the first thing is I'd like you to just discount these two columns over here. This is the actual calculations you'd be doing if you were calculating the result. We're not interested in that. We're interested in the 11 years and the average rainfall for July for each of those years. So in 2001, we can see that the month of July had 55.1 millimeters of rain. If we're actually analyzing this data set, we can see that 2010 was the driest July out of the 11 years at 10.8, and the wettest July was 2002 at 95.6. Okay, now there's one further bit of data that's really important. We have 11 years with the total, not the average, the total rainfall for the month, and we could calculate what is the actual average rainfall for July. And to do that, we'd have to add up the total for each of the Julys across those 11 years, and would get this number down here, 54.45. Now, why do we need to know the average, or the mean as it's mathematically called? Well, it allows us to determine what should we expect on average in the month of July if we're in Cambridge. Well, we should be expecting 54.45 millimeters of rain. And why is that important? Well, if you think about all the different industries dependent on water, for example, agriculture or water supply companies, they're all going to need to know approximately how much water they can expect on average to come out of the sky. Okay. In a year, for example, in 2010, what's clear here is, sorry about that, is that significantly less water arrived in the month of July, which might present a problem for all kinds of different people, both individuals thinking about the amount of water falling in their back garden and their plants, and how that might affect their growth, to farmers on a much bigger scale, to water companies providing water, to hydropower stations, and so on. Likewise, 2002, they achieved significantly higher than that average. Now, what we would like to do, and why the standard deviation is a very useful statistical test, is we'd like to know approximately most of the time what is the likely range we're going to get around the mean. Obviously, the mean rainfall has never fallen. There is not a single year of those 11 years that has 54.45. The closest we get is 2008 with 52.1, which had slightly less rain than that average. So what we'd be really like to know, and 2001 had slightly more, is what should we expect? And standard deviation can predict what we should expect 68.5% of the time, which really, for every 100 years, 68 years or 68.5 of those years, we should get a rainfall between a set of values. Okay, so I'll talk a little bit more about what that looks like in a minute. So what we do is we calculate the standard deviation and we do the statistics on these, and we get this number here, 20.21. Now, what does that really mean? Well, it means that the standard deviation from the mean, and that's an important word there, is 20.21 millimeters. What does that actually mean? Well, if we take 20.21 away from 54.45, and we also add 20.21 to 54.45, we get the range around the mean of likely rainfall 68.5% of the time. Let me just have a little look at what that means. So we have an answer to that question here. So what should we get? Well, 68.2% of the time, or if we put it in a different way, 68.2 years. So that's, or simply 68 years out of every 100, rainfall will lie between 34.24 and 74.66. Where did that number come from? Well, all we did was we took the 20.21 away from the mean and we added it to the mean. Now remember, the mean was 54.45 and the mean was the average rainfall falling across the 11 years. That's a really useful kind of number to now have, that we can predict that 68% of the time in the month of July in Cambridge, the rain is going to lie somewhere between this number and this number. Now, if we want to know 95% of the time, well, all we've got to do, that's 95% of the time, is what we call two standard deviations. So two standard deviations would be 40.42. That's just this number here doubled. And we just take that away from 54 and we get roughly 14. Likewise, if we add it to 54.45, we get 94. So 95% of the time, the range will be between 14 millimeters of rain and, if I add 14, 94 millimeters of rain. We can actually go even further and say what 99% of the time, because that is three standard deviations. So that's three of this number. Now, three of this number is over 60, and take away 60 from 54, you get a negative number. You can't have negative rainfall, so clearly that would be 0. But if we added 60 to 54, we get a number of 114 approximately. I could round that up just a little bit. So 14 millimeters is the limit of rain we're likely to get in July 99% of the time. So 1 year out of every 100, we would have something more extreme than that, but 99% of the time, we have within three standard deviations, and 68.2% of the time, it falls within one. And that's why you do standard deviation. It's a very useful, predictable result to try to work out what your range around the mean is. So that's me answered the two first key questions, which we just look back at here. We've got the result. We didn't have to calculate it because you don't need to do that. But what does that result mean? What can we expect 68.2% of the time? And that is just the result, the one standard deviation. Now, why is this test suitable? Well, let's just have a quick explore of that. You will also find another tutorial that explores that in a lot more detail. But why is it suitable? Well, there's a number of reasons. First of all, it's one of the most important descriptive statistics we use. Like interquartile range, it allows us to mathematically describe a data set in terms of how spread it is around a mean value. Now, if the one standard deviation is a very small number, for example, it's maybe 3 or 4, and the mean was 50, that means my range would be, let's just say it was 4, my range would be between 46 and 54, 68.2% of the time. If my number was very big, like 20, then my range would be much bigger either side. So it can tell us whether our data set is quite clustered around the mean or quite dispersed around the mean. And that really just depends on how large our number is. It is also a very useful predictive tool because it allows us to predict what should be happening 68.2% of the time. And in the case of our example, we can expect this range in rainfall between these two numbers 68.2% of the time in the month of July. And that's very useful for a number of industries. As a matter of fact, it's very useful for all kinds of reasons. If you're able to predict a range of possible results mathematically, you can probably see that that's useful for things beyond geography. What else? Well, it's much more accurate in terms of its calculation than interquartile range, because it takes into account all of the data set, whereas interquartile range just looks at the range of the middle 50% of values, whereas standard deviation weights the extreme values in the data set. That's the numbers on either end of the range in a lot more detail. Okay, and as I said a second ago, it shows us the degree of difference or variance. So that would be around the mean. So that's just how big is that one standard deviation result. In this case, it was quite a large result. 20.21 around the mean of 54.45 is quite a big spread out data set. And when we look at the actual numbers, we can see our range is quite large, from 10.8 all the way up to 94.6. And our mean value, 54.45, does have a couple of values very close to it, 2008 and 2001. And it has another few values that are reasonably close, like this value here, 59.3. But actually, we can see that the variables, the rainfall totals in July, do vary quite significantly, which is why our standard deviation number is quite big. So this is quite a varied result. It's got a large variation around the mean. Whereas if this result had been something like 2 or 3 millimeters, it would have suggested that most Julys have a very similar rainfall total.